Assalamualaikum warahmatullahi wabarakatuh. My name is Nissan Jia binti Muhammad Razi. My matrix number is 2011711736, and today I will be presenting about tissue engineering. So for the introduction, tissue engineering is the use of a combination of cells engineering and materials methods and suitable biochemical and physicochemical factors to improve or replace biological functions. So the term has also been applied to efforts to perform specific biochemical functions using cells within an artificially created support system, such as an artificial pancreas or a artificial liver. So process of tissue engineering, firstly we start by building materials. For example, extracellular matrix, biodegradable polymer, shape it as needed, and then seed it with living cells, and then bath it with growth factors. Cells multiply and fill up the scaffolds and grow into three-dimensional tissue, and then we implant it in the body. So cells recreate their intended tissue functions. Blood vessels attach themselves to the new tissue, and then the scaffold will dissolve. So the newly grown tissue eventually blends in with its surrounding. So what is tissue engineering? Tissue engineering is a set of techniques to produce tissue primarily for repair or improvement of human body functions. There are also some additional spin-off applications such as screening of pharmaceutics and artificial meat. Tissue engineered constructs are different than medical implants, which are technical devices made from man-made materials without living tissue parts. And then tissue engineering also. Tissue engineering can be done in firstly petri dish, simple method, commonly used in tissue culture. Bioreactor, simulate the body conditions like gas, temperature, pH and dissolved oxygen levels. So applications for tissue engineering. Firstly, tissue engineering covers a broad range of applications. In practice, the term has come to represent applications that repair or replace structural tissues, such as bone cartilage, blood vessels, and bladder. These are tissues that function by virtue of their mechanical properties. And then a closely related field is cell transplantation. This field is concerned with the transplantation of cells that perform a specific biochemical function, such as artificial pancreas or an artificial liver. Tissue engineering solves problems by using living cells as engineering materials. This could be artificial skin that includes living fibroblasts, cartilage repaired with living chondrocytes or other types of cells used in other ways. So the pros is firstly help a person conquer a disease or illness, and then person will go through fewer surgeries, no chance of rejection, people would not have to wait for an organ donor, people also would not have to donate their organs after they die, because they usually donate after they die, right? And then this technology could lead to even greater technologies in the future. And then it is also a permanent solution. And the cons is medicine researchers face many difficulties in constructing suitable scaffolds. It takes a lot of research and understanding of each organ and tissue. Ethical issues, so cells have to stay alive inside the body and continue to function, which is difficult for researchers to discover for complex organs. And the properties of the recommended polymeric biomaterial PLGA are commonly used to treat patients with organs or tissues that have been damaged or destroyed. They have demonstrated their biocompatibility, their deterioration into non-toxic products, and a long history of use in degradable surgical structures. PLGA degrade via hydrolysis of ester bonds. When degraded, natural pathways eliminate the monomeric components. And then properties of PLGA, the advantage and the disadvantage: excellent cell adhesion and proliferation, good mechanical properties, features faster degradation than either PGA or PLA, wide range of degradation rates. So the disadvantage is poor osteoconductivity, may develop biocompatibility problems. And then rationale for PLGA: PLGA is biocompatible and biodegradable, exhibit a wide range of erosion times, has tunable mechanical properties, and most importantly, is a FDA approved polymer. So PLG has been extensively studied for the development of devices for controlled delivery of small molecule drugs, proteins, and other macromolecules in commercial use and in research. Also, PLGA depend upon multiple factors including the initial molecular weight, the ratio of lactide to glycolide, the size of device, and storage temperature. Example of stimuli responsive biomaterial used in cartilage tissue engineering. Hydrogens can be engineered so that their physical-chemical properties such as their stiffness and porosity can directly influence the phase of the encapsulated cells, including their migration and differentiation. And then furthermore, stimuli-responsive hydrogels could improve the in vivo therapeutic efficacy and also provide new therapeutic pathways. That's all from me. Thank you.